Welcome to constexpr all the things. This, as I'm sure many of you know, is Jason Turner. He is an independent contractor and trainer working out of Denver. He does C++ Weekly on YouTube. He is one of the co-hosts of CppCast, along with Rob Irving. He speaks at lots of conferences, and he finds time to do all sorts of things besides.
And this is Deane, who is a principal engineer at Blizzard. Been working in gaming for 20 years, most of it in C++. He is a functional programming geek, which will definitely come up in this talk.
A little.
A little. And you're on the Battle.net team.
That's right. All right, so in the interest of not hiding anything, when I first heard about constexpr, this is what, and about user-defined literals, I thought, this should be possible at some point. Can we embed JSON literals in C++, have them work at compile time, and have them control configuration in code? That's one example. And this, I think, is a great bellwether for what constexpr can do. So when I first heard about constexpr and about user-defined literals, I wanted to do this. JSON is ubiquitous. JSON is used for a lot of things. It's very useful. It's very well known. It's simple, but it's also recursive, so it's sufficiently interesting to try and do this with. Oh, you want me to do? Yeah, OK. Sorry, we did this differently in Aspen. So, of course, the promise of constexpr is that we get runtime efficiency by moving things from runtime to compile time. Also that we can simplify code through compile time computation. So where we would have magic numbers in code, perhaps, we could now just write the more expressive expressions that we use to compute those magic numbers, and they get done at compile time. We don't need to muck about with the preprocessor to be sure of things not making it into the runtime. And less cross-platform pain is nice if you can move things into the compiler that were previously in some other step in your tool chain. So if you can do things constexpr-wise now using the compiler rather than, say, generating code to produce your constants or whatever, that's nice. And if you're working cross-platform, reducing steps in your tool chain is very nice. So moving very quickly along, just a quick recap of where we are with constexpr up till now. So there have been 3 ages of constexpr by my thinking. C++ 11 was very limited. We had one return value per function. We had to do everything with extreme recursion. And we saw things like math functions, fnv1 string hashings, you may have seen. This very kind of this linear recursive technique down a string, something like that. And then when C++ 14 comes along, we get generalized constexpr, so we're no longer limited to this kind of very recursive technique. We can write more straight line C++ code that we're used to. And we get, because of that, we get some constexpr libraries appearing. We get MoMA3 hashing instead of fnv1 hashing. And now we're at the dawn of C++ 17, and we have some more features available in constexpr land. One of them is if constexpr, and that's going to is simplifying and will simplify metaprogramming a lot. We get a lot of constexpr stuff in the STL, in particular things like string view, which are more or less born into constexpr world. We get constexpr lambdas. That is that the lambdas have their function call operator now as constexpr. And who knows, we might get constexpr by default on a few things. But one of the problems with constexpr up till now is that you can't tell when you are evaluating, when you're in the evaluation of your function, you can't tell whether you're being evaluated at compile time or at runtime. And this is something we'll touch on a bit later. We'll come to talk about some proposals that deal with this and some other things constexpr-wise. But this fundamentally is one of the main problems. Even if you write nice constexpr code, if it doesn't get evaluated and assigned to a constexpr variable, there's no guarantee it'll happen at compile time, and it might accidentally be omitted in your runtime. And you can try things. There are various things you can try, like Sphene on constexprness. It tends to be a little bit brittle and certainly a lot more code than you probably want to take on. But we'll touch on more stuff later on. So take it away, Jason, for the next part.
All right. So this is effectively a JSON value that we want to be able to parse that we were just showing. So we've got the problems of how do we represent JSON values and how do we parse them at compile time. JSON is a discriminated union of null, Boolean, number, string, and an array of values. And also object types, which is a map of string to the values. So we're going to need some sort of recursion in our parsing, and we're going to need constexpr ways of dealing with string, vector, and map. And, well, all that turned out to be a little bit easier than I think we were afraid it was going to be. But we will get there. Constexpr strings. Now, interestingly, C++17 adds standard string view. I have a hard time with using this in a lot of constexpr contexts because I feel like it is, it's not intended for storing a string, and we're talking about storing strings. And it can only hold literal values. We can't build strings. So we need some way to pass and store strings in general, work with character string literals. And so string view, like I said, it would technically work for some of these things. Again, I feel like it mixes metaphors. Don't like using it for compile time stuff. So we built up the static string class, which looks like this, which uses a templated array constructor to pull in the data from a character literal, that is. And we can make all of our methods constexpr, and it's pretty straightforward. Although, and not directly related to this talk kind of way, when I've gone back and looked at this talk, I have noticed that there's something kind of missing from these slides, I think, from these lines. Does anyone have any comments on what we could add to these declarations for our methods? Anyone? You have to talk to us. Yeah. What's that? Am I slicing? Oh, no, I don't mean add a new method, just in the declarations of these methods. They could all be no except. I just want to point that out. But we didn't make them no except.
Right. But we doubled them up for no except, right? Because it's part of the type system?
You wouldn't have to double them up here, but we do have other stuff. And so not all constexpr methods are no except, but many of them can be. So our vector ends up looking like this, where we're just taking advantage of the fact that C++17 now has a constexpr-enabled standard array. And we have our data and our current size. Iterators, pushback, and all this is pretty easy to write. We just push something, add a value to it and increment the size. Does that make sense?
Right. And the size is fixed.
Yes, the maximum size is fixed. So that as a template, and you can see right there it says size equals 5. That becomes a problem in a minute.
In the early slides, you'll see limitations. You'll see, we'll get to hopefully removing some of those limitations later.
Yes. So as we can see on the pushback here, oh, that was weird. If our size grows beyond the maximum size that's allowed by our templated size type, we throw an exception. And this is perfectly fine in constexpr context, because if it were to throw the exception during a constexpr evaluation, then it would fail to compile.
Right. And in fact, if you didn't have the throw there and you went beyond the array size in a constexpr context,
you would still get a compile time error.
You would still.
Yes. Because if you try to index past the end of an array in a constexpr context, you get a compile time error. Also, but this allows us to work with it both in a constexpr and runtime context, possibly.
Right.
So also, it's interesting to note here that we were not able to use StandardNext for incrementing here. So we can see, using this little tool that some of you may have heard of before, Compile Explorer, that there's a bug in GCC 7.2's implementation of StandardNext that it's unable to increment because of its iterator category. But these things are fixed in trunk.
Yes, I believe so. So yes, so next, advance, which I think Next uses, and distance.
Distance, yes.
They are all constexpr in the standard. They just happen to be a bug with them in the current GCC 7.2 that we're using today.
Right. So now we can naturally use our constexpr vector like this, or more to the point, like this. We can write a constexpr function, and at compile time, populate our vector, assign it to a constexpr variable in our main, and then actually do a compile time check with static assert to prove that we did, in fact, add something to our vector. Is this cool with everyone? All right. So now that we have a vector that we can use in a constexpr context, we can build up strings. So we can, building on the model of how the standard library's basic string is built, implement our own basic string. That inherits from our vector and simply, builds a string out of it. We have done a little bit of a cheat, in that all constexpr member variables must be, or all member variables of constexpr types must be initialized. So we know that the underlying array is going to be initialized to all zeros. So we've taken the cheater step of knowing that we're going to have a null terminator at the end of our strings automatically for us. And we have not yet provided any methods for shrinking the strings, but that should be easy to do. And then continuing from there, we have our constexpr map, which we needed for our JSON type here. And we did, maybe it shouldn't be called map. It's more like unordered flat map or something.
Yes. Ordered flat, no, yeah, unordered flat.
It's unordered. All of these are linear searches, but they all happen at compile time with small objects. It's kind of irrelevant.
It's a map implemented as a vector of pairs.
Yes. So it's a vector of pairs, as you said. We have std array, and yeah, we'll call that out.
Yeah. So anytime you see a CX qualification namespace here, that's our constexpr namespace. That usually indicates that there was some limitation we found in the standard libraries implementation, in this case of std pair. It meant we couldn't use it constexpr.
That's unfortunate. So then this gives us the ability to do something like this. Oh,
I fixed it.
Oh, okay. So we can have our constexpr map of colors with names, and then we get an actual compile time error on the last line of our main, because we tried to look up a key that doesn't exist, and we're evaluating this in a constexpr context. This is, I feel like, personally, in some ways, equivalent to or almost as good as an enumeration. An enumeration is also, in a way, a magic value of a string that's all checked at compile time, anyhow.
Jason is looking for arguments. You can come see
I am
him
looking
later.
for arguments. Yeah, you throw stuff out here at me. That's how I roll. Anyone want to argue with me? Oh, all right. So why not standard pair? Again, Compiler Explorer is showing us why it's failing to compile here. Non-constexpr function, this is it's scrolling off the edge. The assignment operator of standard pair is not constexpr.
Right.
Which is terribly
not
disappointing.
in the standard.
Yes.
I think.
Yes, this is not a bug in this particular implementation. It is simply not specified as being constexpr, and as far as I know, it totally could be. Do we have any standard library implementers that wants to argue? All right.
I guess Marshall.
Yeah, Marshall's not here.
But this is actually, to touch on that, that's a sort of common thing right now with constexpr in the standard. There's a lot of places where, maybe not a lot, but there are places where things that should, by our thinking, be able to be constexpr just aren't specified as constexpr in the standard. And it's just because nobody's got around to it yet, nobody's done a proposal, nobody's quite thought about it in that way yet.
Some things it's like a weird little hole, like everything about standard pair except for the assignment operator.
Right. And of course, if you have a standard pair with two things that are constexpr, you can do dot first assign and dot second assign, and effectively you have assignment. So to not have assignment operator on the pair is probably an oversight.
Yeah. So we needed some sort of a find to implement our map, and does anyone recognize this find if? Yeah, I mean, this is literally how it's specified, like in the standard. This is taken straight from CppReference.com. The only difference is it now says constexpr in front of it. None of the standard algorithms in the, one, min element, max element, min and max are constexpr. The rest are not.
Yes, and once we have find if, of course, that's what makes the map work.
Yes.
The constexpr map.
Right. So then we've got Bryce here. Let's see, reviewing code I wrote last week, I found 3 implementations of constexpr transform. Constexpr algorithms, please. And we totally agree with Bryce.
Yes. But he won't let us have constexpr parallel algorithms.
We can have constexpr parallel algorithms. May as well.
It's just the compiler implementation detail, right?
Yeah. We're not worried about what the compiler has to do.
Yeah.
All right. So we also had to implement mismatch, equal, and copy, and found uses for several of them, as the slide says here. I was recently playing with some more constexpr containers myself on the flight here, and implemented everything necessary to do a sorted container. And it's, again, just taking the implementation straight from CppReference.com, adding constexpr to the front of it. Works just fine. So we end up with this, which is our recursive declaration of our JSON thing using our CX vector and CX map and our static string that we were just discussing. Now, I completely lacked the imagination to actually figure out how to implement this. And Ben had the idea for our first attempt here. It gets better. But as you can see, hopefully, this has the max depth specified in the template argument on the first line. And that means we are specifying that this is going to a max recursive depth of 5. So you could have at most 5 nested elements in your JSON thing. And this was expensive at compile time.
Yes, it gets to be kind of expensive at compile.
Yes.
This is the simplest thing I thought of that could possibly work. So this was kind of the proof of concept that we went through.
Yeah, he threw it out there, I implemented it, and I'm like, that's amazing, it works. I, like I said, lacked the imagination for it. Yes, go ahead, sorry.
Can you go back to slide?
Absolutely.
Is there any reason why you didn't use union there?
Oh, why didn't we use union
That's
there?
the one thing I didn't fix because I wanted to give you the opportunity to explain this.
And I forgot about that. We are using union now.
Yes.
We weren't, because there was a misunderstanding between myself and the compiler for what was allowed to be initialized and modified at compile time in a constexpr context with unions. It can work here, yes. Yeah, the implementation on GitHub is still union, right? Because I thought you had one more.
We are using union now. Yeah.
Okay. I knew we were, but then I thought you had another misunderstanding again with Clang later, once you tried to update it to Clang.
I don't think so. Not for that, at least.
Okay, cool. So yes, you could use union here, but you have to be just aware of the fact that everything has to be initialized in constexpr member variables, and that comes into play with a union because a union by default is not initialized to anything.
Another question.
Oh, sorry. Where?
So when you were taking the containers, like you said on the flight, with adding constexpr from,
Yes.
you also doing structural testing, making sure, because you said you're taking the CVP standard and then converting it to constexpr, and you said everything works. Have you tested structurally and to see what speed is, to see if it's still running about the same speed?
So the question is, by adding constexpr to these things, have I checked to see if they're still running at the same speed as the regular algorithms? I would say I have not, but I can also say I have never seen adding constexpr to an algorithm hurt anything. But I can further qualify that by saying the textbook examples of these algorithms is not necessarily how they're actually implemented in the standard libraries, because I know like some of them, like GCC standard library algorithm implementations, have some like default unrolling built into them and that kind of thing. And these textbook implementations don't have any kind of optimizations. They rely on the compiler optimizer to do them. But no, I just to clarify, no, I have not done any direct comparisons.
And just to be completely clear and transparent, when we say we've made constexpr vector and constexpr map, They are nowhere near what standard vector and standard map support.
Right.
They are just what we need for the compile time parts.
Although we do get pretty far along the way with,
Yeah, I mean,
most of the functions.
They're very serviceable.
Yes. So then we are able to do constexpr, keep building on this and so again, we're taking advantage of the fact that if you were to throw an error at compile time or throw an exception at compile time, that you get a compile time error. And, well, we can access the arrays of things, and we are able to basically do this at compile time, and it works.
Go back one slide.
Yes.
So I just want to point out, so you see toArray here. You can imagine the other functions. So there's a const version, non-const version. They return const ref or mutable ref to the underlying thing. As for toArray, so for toObject, to Boolean, to number, to string.
Yes, right. Yes, this is just a tiny snippet of all the things. So, yeah, we looked at that, sorry. Why not variant? We touched on this already. Similar to pair, it's missing a couple of key things that are kind of critical. We don't have a constexpr copy constructor for variant, a move constructor, or copy assignment or move assignment operators for variant.
Right.
And this comes down to the fact that variant wants to do placement new, basically, for these things. And
that's not allowed at compile time.
It's not allowed at compile time. There are ways to work around it.
I don't know.
There are.
Yes.
They also, so it's an interesting side note, but I should probably move a little bit quicker here, that the standard does guarantee that if all of the things inside your variant are trivially destructible, then it is also trivially destructible. And it takes a little bit of gymnastics to implement that.
Right.
But there's no reason why we couldn't make some of the same calculations for if they're trivially default constructible and that kind of thing. So, real quick, all the requirements for our compile time types, if you're looking in the standard, these are known as literal types. They must have at least one constexpr constructor, and they must be trivially destructible. So that's it. When you're thinking about deploying constexpr in your code, that's what you have to worry about. So as we've already mentioned, we've got some shortcomings in array, string obviously can't be used in a constexpr context.
Right.
String view can't grow or change. Pair and optional and variant have the assignment problems. And standard swap is simply not constexpr, which that one confuses me a little bit too.
And some of these are shortcomings in the actual standard, and some of them are just, as we saw, some implementation things. But yeah, for swap, we don't see a reason why it shouldn't just be defined constexpr.
Unless it comes down to some sort of no accept guarantees or something, but that should be something that can be worked with then for sure. So our containers have a fixed maximum size. They currently can't shrink, and they require all the types that are default constructible. Since we have to default initialize all the things inside of our containers, they must be default constructible. So we're almost to the parser, right?
Mm-hmm. We've got a few more slides.
So we could, one option for making our containers so that they don't require things that are default constructible is that we could put an optional, like make basically arrays of optionals of things, and then they wouldn't have to be initialized, and then we could initialize them on will when we needed to. No, stood optional, well, it's constexpr constructible, but not assignable, I believe, because it comes down to placement new again.
Yeah, but don't you move the problem into the implementation stuff then?
Oh, no, I mean, we have our own implementation of optional also. That's, I believe, a tiny typo here. We could an optional-like thing. Is that good?
Right.
So, yes, and it's...
This is your next slide.
Okay, right. I like the idea of being able to make all of the standard constexpr. So this is CppReference.com for what is required for a minimal allocator. And there's nothing in here that inherently couldn't be constexpr. So I say we just make these things constexpr like we have been doing, or at least make them optionally constexpr. And well, that's left as an exercise to the reader. Just go out and make your own constexpr allocators, roll it into one of the standard containers, and let me know how it goes.
That may be happening for some people. We'll come back to that later.
Yes, we will come
but
back
for
to
now,
that.
let's tackle the other problem. So Jason just talked about how we actually represent JSON values, right? So we've got some idea of how to do that with a recursive template. So the kind of the half that fell to me was how do we parse these things? How do we turn string view literals into JSON values? And so to answer that question, first we have to answer the question, what is a parser? And if Dr. Seuss had been a computer scientist, he might have said something like this. A parser for things is a function from strings to lists of pairs of things and strings. This quote is from Fritz Ruhr, who's a functional programming lecturer at Willamette University. So at the top here, you can see I put a Haskell function signature, and you'll see in a few slides coming, you'll see the odd Haskell function signature. If you can read it, great. Haskell's a great language just for specifying function signatures. But this just means the type of a parser of A, and A is like our template parameter, is a function from string to list of pair of A and string. Now in C++, we might say something like, what's on the bottom? This is a template alias, which is a function. But there are a few things wrong with this C++-wise, because we don't really quite mean list or string, right? Or even function. When we say string, we'd much rather say string view, because that's constexpr. It's a compile time string-like thing. And when we say list, well, what the list represents here in the parse is that you might have multiple ways to parse something. So we're just going to condense that down to optional, meaning the parse can either succeed or fail. And we can do that in constexpr world, using our own kind of optional thing that works. And when we say function, we mean, of course, something invocable. And in C++ 17, we mean constexpr lambdas. So let's look at a very simple parser that we could make. So on top here, I just have some aliases that make life simple. So a parser input is a string view, and a result of a parser is this optional of a pair of thing and rest of string, right? So you parse the thing out of the string, you've got some rest of string to work on, and you've got your t that comes out of it. So that's what input t and parse result t are. So match char here, we pass it an input and we pass it a char, and it's going to return us the parse result. And the way it's going to do that is you can read the code, it's very simple. If the string's empty or doesn't match the char, we fail, and that means returning null opt. Otherwise, we just return the wrapped up pair of the char that we parsed and the rest of the string view. I hope that's clear. Now, but if you're paying attention, you'll note that match char isn't quite yet a parser, because we said that the signature of a parser was parse input t to parse result t, and this takes the char as well, right? So it's not quite a parser. But we have constexpr lambdas, so what we could do is capture that char and return the lambda, which is itself a parser. And that's what this is. So now make char parser will make us a parser that matches the character we give it. So we capture the character in the lambda, and what we're returning is a lambda, which is a parser, because it's a function from string to list of pair of thing and string, so optional pair, right? So this code on this slide is exactly the code you saw on the previous slide, but just put into a lambda, and it's now capturing the character. So make char parser will give us a parser for any char that we give it. So now that we can do that, we can think about some other sort of primitive parsers. So far we can make a parser for chars. Fundamentally, parsing works on strings, so we're going to want a few more things. It's going to be useful to match any one of a number of chars that we give it. And so here is this function, one of. Again, it returns a lambda, It's returning a parser. And it's just doing, the kind of obvious string. You see if the thing at the beginning of your input is in your set of string, your string view that you captured. So that, I hope, is clear. Similarly to one of, we can write none of, which I'm not showing the body of, but it works exactly the same way, only the logic's inverted. You're just checking to see if the thing at the beginning of the string view is none of the things that you captured. And also we can make a parser that matches a whole string just by capturing that string and doing the obvious thing to check the string view. And that uses a constexpr stood mismatch. So everything clear up to this point? Everyone happy with parsing chars, parsing strings, etc.? All right. Now we have these kind of primitives. Now we can think about ways to combine them together to build up towards parsing greater things. And some of the things we're going to want to do here might start to look familiar if you know the kind of functional patterns involved. One of the things we'd like to do is change the result type of a parser. So right now we have a parser for chars. If that char represented a digit, we might want to change it into an integer. And so we want to put a function in there that we know how to write a function that changes a single digit to an integer, and we want to apply that to our parser that parses chars to make a parser that parses integers. So we can write that function. These are kind of parser combinators that we want to write to fold things together. We might want to run one parser and then run a second one based on the result of the first one. We might want to alternate two parsers, so try one, and if it fails, try another one. And we might want to run two parsers in sequence and then combine their results together. So I'm not going to go deeply into the functional programming aspect, but if you know these patterns, they'll look familiar. So this is fmap. This is the thing that changes a char into an int, for example. So it takes, and again, the Haskell type signatures are at the top, if you're familiar with those. But it takes fundamentally the function f and the parser p, and again, what it's going to return is itself a parser, a lambda. And what we do is capture the function and the parser that's kind of we've got to change. We run the parser that you can see on this line. If the parser fails, then we have to fail. But if the parser succeeds, all we do is run the function on what it produced, wrap that back up in our thing and rest of string, and return that. So that's fmap. Similarly, we've got this is alternation. So this time we take two parsers, and the bit of template metaprogramming at the top just says that they're going to have to return the same type, because what we're building has to return either one, and we need to know what type to return. So we take two parsers, P1 and P2, and we return a parser that in its body just says, try running P1. If that fails, if that succeeds, you're done. But if that fails, try running P2. And the thing at the bottom here is just a useful thing for building up combinators, which is the parser that always fails. So you can make it be of whatever type you need, right? So it's just gonna always fail and return null op. That turns out to be useful in some cases. So that was alternation. The final kind of primitive combinator that I want to show you is, I called it combine, for lack of a better word. But what this does is instead of trying one and then diverting to the other, this runs one and then runs the other one in sequence, takes the two results, combines them. And this turns out to be very useful. So you can see what it's doing. It's saying const auto R1 equals P1 it's running the first parser there. If that fails, you fail. Then you run P2 on the leftover string from P1. You've run the first parser, you want to run the second one on what's left over. If that fails again, you still have to fail. Otherwise, you just return the result of calling the function on both results. So it's a way of running two parsers in sequence and then combining their outputs to make a parser for the output of the function. So this turns out to be very useful. There are a couple of very useful patterns of this, and it's useful for when you don't care to save the result of a parse. So you just want to say, something like, well, I know there has to be a comma here, but I'm not interested in the comma. I want to see the next thing, right? So I'm parsing something, and I know there's going to be a comma, but the comma's not going to be part of my output. It's the thing I'm interested in, let's say. And so you just want to throw away either the left-hand side of the parse or the right-hand side. And so what I did was I overloaded operator less than and operator greater than just to do this combine pattern where you throw away the thing on the less than side, if you like, or the other way around on the right-hand side if you're doing greater than. So you can see that when we call combine here, we give it the parsers. The function we give it just throws away the left-hand argument and returns the right-hand. Okay, a few more combinators. And now you can start to see perhaps what we're building up to. Now I'm just showing you the Haskell type signatures for these, but maybe you can imagine kind of having seen some of those C++ bodies, how these might be implemented. And the thing these have in common is they're accumulation style. So they work in the same way as std accumulate. Many takes a parser and an initial value, that's the b, and then it takes a function that folds the result of that parser into b's, and what you get is a parser of b's. Right? So it's very much like accumulate. You give it initial value, you give it a function to combine values, and what you get out is the final value. Only this time it works on parsers. So many will match 0 or many runs of the parser. Many 1 matches at least 1 parse, but again, potentially unbounded. Exactly n, you can probably guess what that does. It takes the int argument as its second argument, and so it runs a parser exactly n times, combines the results together. And then separated by, you can see where this is going perhaps, it takes 2 parsers, one of which is kind of your parser for things, and then the parser x here is like the in-between parser. So if you're parsing a list of things in JSON, you're going to want to parse value, comma, value, comma, value, comma, etc. And that's what separated by does. So it'll parse values separated by parsing commas. And again, the initial value and the fold function, and what we get out is the result. So I'm not going to give you a wall of text for the C++ on these things, but given what we've talked about, maybe you can see that these can be implemented. All right, so let's take a look at a couple of parsers, just so you get a feel for what these look like. This parser just eats white space. It's one of the simplest parsers we can make. And it eats, just a very limited subset of white space at that. So space, or tab, or new line, or carriage return. Those are our char parsers. We're alternating them all together with the bar operator. And then we're saying the white space parser is many of those. And the accumulation function, we don't care to catch white space, so we're just passing through monostate and throwing away.
So C++ 17 makes lambdas enabled for constexpr use.
That's correct.
How much more code do you think it would have taken without being able to use C++ 17's lambdas here?
To be honest, I don't know that. I don't know if it would even be possible. You'd be talking about simulating lambdas by returning local structs from functions or something, or templates.
Yeah.
I don't want to think about that too much.
Okay.
But an important thing to note there is if I go back a few slides, so you can see that all of these functions returned lambdas, but there isn't actually a constexpr there on the lambda itself, and that's because one of the defaults, for lambdas now, lambdas are by default constexpr, unlike regular functions. So you don't actually have to put the constexpr keyword in there.
By default, if they meet the requirements of being constexpr.
Correct, right, if they can be constexpr.
Which one wonders why we don't do that to all the functions at this point.
Right. Okay, so that one eats white space. This one parses a decimal integer, a positive decimal integer. And so what we're doing here is building up the parser combinators. We're saying 1 through 9, because the decimal integer won't start with a 0. And we're going to bind the result of that and pass it into the function that we pass, which, so 1 through 9 will be that char x parameter to our next function. And then inside of that, we're saying, well, after you've parsed that 1 through 9, do many of 1 of 0 through 9. So you can have any of those digits many times after your initial digit. And then we're accumulating in the obvious way of shifting and adding. So that, I hope, is clear. Here we have a very simple string parse. A parser for strings is basically you parse a quote, followed by a bunch of things that aren't a quote, followed by another quote. And you can see at the bottom here, that's where this greater than and less than operator overload gets to be really nice, because that's all that's saying. It's saying, do a quote, throw away that, do the string parser that's not quotes, keep that, and then do a quote parser afterwards and throw that away. All right, so now we're getting towards a toolkit for building JSON parsers. Because JSON is a discriminated union, a reasonable attempt to parsing it is to have parsers for 6 different types of things and alternate them together. And so that's what this does. It's a bit of a wall of text, but you can see there's basically 6 or 7 different alternations here. You can see there's a parser for null in there, there's a parser for true and false, there's a number parser, a string parser, and then an array and object parser. And we're doing a skip white space before we parse a value, so that all gets stripped out. Now, I need to speed up, don't I? Yes, that's the rest of the previous slide. There's array and objects are parsing key values in that we're using that separated by parser. Now, all of these at this point are function templates, right? Because our JSON object is itself a template, and in order to be able to parse a thing at any depth of the tree, we need the equivalent function template instantiated at that depth, or for that depth. So that, as it goes, actually works. And that was the simplest kind of proof of concept. This was how we knew we were on the right track. For suitable values of works, which is to say limited recursion depth and limited array size and object size. It's got a few problems. So problem number 1 is a JSON number isn't just a simple decimal positive integer. It's this thing. This is from json.org. But actually, if you look at this and think about our combinators, we have all the toolkits, all the things in the toolkit that we need to write a parser for this. It's just a little more complicated than I can put on the slide for you. But it can be done. Similarly, a JSON string isn't actually a string view because it's got escape characters. And in general, you don't get a one-to-one mapping of input to output. You can't just say, oh, parsing a string is just taking a subset of my input string. And it's this thing. But again, we have all the parts we need to build a parser. And with JSON's string, the constexpr vector string, we have the ability to put our output separately from our input. So we can build this. Again, it's a bit too much to show you, but you can imagine how this can be built. Problem 3 is a little trickier.
Yes.
What kind of compile times are we seeing at this stage?
Minutes, at least.
Yeah, it was, I mean, it worked, but it wasn't nice.
Yes.
So, and problem 4 is, even if we get past problem 3, this is pretty much a killer for any kind of actual use, right? You can't just say, oh, by the way, your strings can only be so many characters, or your depth can only be this much, or you're not allowed more than 6 things in your array.
I think that's 255 characters should be enough for anyone.
Right. All right, so we need to get rid of templates. So this is a reminder, so this is part of our JSON value. So in our vector and our map, we're recursing the templates using the depth -1 parameter. So we just built a parsing framework. Why don't we use it to help us solve this problem? What we're parsing out right now is the JSON value, but we don't have to parse out the value. We could make a parser that returns the number of values that will be required to store the object. And that actually is easier than parsing the object itself, because all we do is reuse our kind of structural code that knows how to parse strings and numbers and all that stuff. But instead of actually outputting the values, we just output the number of values that we'd need. So an array is just one value for the array plus number of values in its children, object the same, everything else is just 1. And we reuse all the structural components, and the number of values parser works. So now that we have the number of values parser, the JSON value doesn't need to be a template anymore. That's coming up. Okay, so the struct itself, the kind of the struct recur that was holding all our parsing functions, that was enabling us to do mutual recursion on the parsing functions. Now, instead of the functions being templates, the struct itself is a template that just knows how many values we're going to need, and we'll use our compile time vector. And then the JSON value itself is no longer a template either, because inside the vector or the map, instead of having the next level depth objects, all we need to do is store the offsets into the externalized storage. So to help you understand that a little bit, here's an example kind of how the object layout happens. So if we're parsing this array, and it's got 3 elements, and one of those elements is itself an array, the object layout comes out like we see here. So the element 0 is an array, and its children are elements 1, 2, and 5. Those are actually offsets from itself. They aren't absolute offsets. So you can see that at position 2, we've got the child array, and its children are offsets 1 and 2 from it. And so that's kind of how that works. And then to drive the parse, to figure out the number of objects ahead of time, we need this. This is actually a GNU extension right now. GNU and Clang support it. So it's this templated operator quotes for the user-defined literals. This is N3599, I believe, was the proposal. It's not in the standard yet, but it is implemented by GNU and Clang, GCC and Clang. And there's no real reason it shouldn't be in the standard, especially since it enables things like this.
And there are other ways of declaring your string literals, but some of them we couldn't get them to compile, even though our reading of the standard says that it should have, I believe.
Possibly.
I think so. It's the
templated. So this is not quite standard because the templated operator for this form of user-defined literal is not in the standard, but it is implemented by GCC and Clang.
Because the type
this
is
particular
templated.
form of the UDL, yes, is templated. Yes. Okay. So, but having done that, we now have solved problem 3 at the cost of an extra pass to figure out how many values we want. We get much quicker compilation. There's no recursive templates anymore. All those function templates, all those recursive function templates are gone, replaced by just plain functions. And that means there's no arbitrary hard-coded limit to the depth of our JSON object, so we can have tests that say things like this, where I just mash on the bracket, and that works. Problem 4, we still have these arbitrary limits on string size, array size, and object size, right? So I thought about this, and I thought, well, can we use the same technique of pre-computing size to get around these? And the answer is, for strings, yes. Because what we can do is, in the same way we're pre-computing the number of values required, we can pre-compute the total string space we're going to need. And we use exactly the same kind of technique to do that. Where we previously have right-sized a value buffer, we'll just right-size a character buffer for the string, and then strings will become effectively string views into that buffer as we parse. And we can wrap up that number of values parser and the total string size parser. They're fundamentally working, they can work at the same time because they're producing independent results from the same pass of the input. They just return the pair of sizes. And so that's what this looks like. So if we have, a JSON object with strings in it, and we've right-sized the value buffer, and we've right-sized the string buffer, then our parse ends up looking like this in terms of memory layout. We've got our values again. For the string ones, you'll see that the strings contain, effectively, the string views into the character buffer. We still have limits on array size and object size, though. And we can't naively get around these in the same way because parsing is fundamentally a recursive thing. It's fundamentally doing a depth-first traversal of the parse tree. And so for that reason, things in an array don't have to be contiguous. You can see in this example that because the second element of that array is itself an array, the object layout is not contiguous. The children of the top-level array are not contiguous. That means we can't represent them naively with offset plus extent. because they could be arbitrarily nested. So again, the answer is we've got a parser framework, let's use it. And we can add another parse to make a parser effectively breadth first. And the way that works is that when you're doing the initial parse over an array, what you're going to store is just the unparsed string view representing that array. All your structural stuff works, but what you get out is not the recursed into values, but just the string view of that array. And then once you've done that for all of the children of the array, then you can go back and do your parsing and put the values at the end where they belong and get all your values and your children contiguous. So with that approach, what we see is this is kind of an intermediate stage of parsing this array. So we've parsed the array itself, the array object becomes the thing at 0, and then its 3 children. So far, we've just parsed out the extents that they have in the string view. And then we can go back, having done this and made our children contiguous, we can go back and in positions 4 and 5, so in position 1, we'll end up with a number 1. In position 2, we'll end up with an array whose children are 4 and 5. And in position 3, we'll end up with number 4. But now you can see that all of the children of an array are contiguous, and so an array can be stored as offset plus extent, right? We don't need to store n values in the array. And we've done that with arrays, so we can do it with objects as well, because objects are just an array of pairs of keys and values, and the keys are strings, and we know how to do strings, and the values we know how to do. So we can apply the same technique that we applied to arrays to linearize the object children. And here's the result of that. So an object is really an array of alternating strings and values. So with all those techniques together, finally we get to the point where no templates and no limits on our recursive depth, on our array size, on our object size. And this is kind of what our final, although the external view is repeated 3 times, which it doesn't need to be here, but for the sake of the talk. But this is kind of the final representation of our JSON value as parsed out by our parser. So I think we're going to run out of time, but the conclusion to parsing is that constexpr lambdas really enable this, right? So that was the whole reason that I was able to build up the parser combinators and actually make this work at all. And they enable a lot more complex literals. So once you have those combinators, you can plug them together in arbitrary ways to parse a bunch of things. JSON is just kind of one example of what can be attacked with this kind of technique. Thanks to that template, user-defined literal operator, which I hope becomes standard, but at least it is in Clang and GCC. You can do multiple parses, and that means that you can effectively solve almost any problem with multiple parses. And I don't know, but maybe there's a concept applicable here.
Yeah.
Now,
up to you if you think we want to do the demo with time here.
I don't want to show you. I don't want to go through all this stuff and then not show you guys, or not show people, the proof here. So I just want to show you that this actually does work. Here is the example that you saw at the top of the talk. So here we've got a JSON object, and in particular we've got a key value here which is feature X enabled true, right? And then I've got an if constexpr which is going to output the appropriate thing depending on whether the feature is enabled or not. And this is everything here is constexpr. Well, stood out, it's not constexpr obviously, but you can see that when I compile this, I'll get either one output or the other depending on whether this constexpr thing is true. So I'm just going to make a shell here, over here, and I think I built it earlier, so I could just run. But you know what? I'm going to actually show you guys how long it takes to compile. I'm in my, okay. Okay, so I'm going to do a make clean. And this is a few years old laptop, and if I hit make, then you'll see approximately how long it takes to compile. And this laptop is not very fast, but you know, it actually built. And then if I run it, where are we? Oh, we're in build.
Yes.
So it's in source, test, it's test CppCon dash demo 1. And it says feature X enabled. And so, as I was saying, and so I have a question for you, Jason, now, because a couple of days ago I started working up a little extra demo, which Jason doesn't know about.
Apparently.
But you know, I was saying that this isn't just applicable to JSON. The question I have for you, Jason, is: do you think it would be useful in ChaiScript, for example, if you could do regular expressions at compile time?
Well, regular expressions at compile time would be helpful, I think, for all of us. I know you had talked about wanting to do that, but parsing regular expressions is not trivial.
And I hasten to add that this is very much a work in progress. But so here I have a constexpr regular expression with a _re literal.
Wow.
And you can see that it's just like the simplest email that you could ever imagine, simplest email check. And here's Jason's email. And now I've got some driver code. This is test code right now, so this is a work in progress. But you can see I've got static asserts that the captured values are going to be JSON and emptycrate.com, right?
This is even more impressive than JSON parsing, and I honestly have not seen this until just
no, this is totally new to JSON. So
you're keeping it real, like live unplanned demos in the middle of the talk.
Well, I had to change something up since Aspen.
Apparently.
So again, I'm going to make clean so you guys can see, so people can see, you know, how quick this is to compile, or at least that it's usable in real life in terms of compile speed.
Yeah.
And then if I run. Well, actually, there is no output, but the fact that it compiled indicates that the static asserts worked.
Yeah. That needs a standard proposal right there, Ben. We all need constexpr regular expressions. Well, okay, so I am going to set a new world record for how quickly I move through 20 slides. And
yes, if people want to go out for lunch, we won't be offended, but
I don't think the right window has
a little more
focus. What do I need to click on here?
Try that.
Okay.
Yeah.
All right.
Okay.
So, problems and things. So you cannot, anything that has a non-trivial destructor cannot be used in a constexpr context. So we're going to do a quick quiz. Is this struct trivially destructible? Everyone raise your hand if you think it's trivially destructible. All right, everyone agrees. Yes, it is trivially destructible. Is this one trivially destructible? We all agree, mostly. Still trivially destructible. Is this trivially destructible? I saw someone go like this real quick. No, this is not trivially destructible because it has a unique pointer inside it, which is itself not trivially destructible, and the automatically defined destructor there is not going to be trivially destructible. Is this trivially destructible? What? Yes, simply mentioning the destructor means it's no longer trivially destructible. So this is not trivially destructible. So,
and it's the same if you put equals default there.
No, if you put equals default, then it is still trivially destructible.
Still trivially? Okay.
If the defaultly defined one would be trivial, then it is trivial.
Okay.
Excuse me. So this matters because if we wanted to somehow create one of our compile time constexpr vectors or something that could grow beyond the allowed space that we specified, we are perfectly allowed to write something like this, where our pushback, now don't actually implement code like this, it's horrible, but our pushback, if it grows beyond a certain size, is able to allocate memory. We can do that if it happens at runtime. We can't do it if it happens at compile time. So this is great. We could plausibly make containers that are highly efficient at compile time and can expand at runtime if they need to. As soon as we add the destructor, the class is no longer constexpr enabled, and we can build this thing, but we are basically required to leak memory because we don't have any way of calling the destructor if it needed to be called at runtime. So there is a proposal out there, I don't have the number for it or anything, where we can do this and say if the body of the destructor is empty, then it counts as trivially destructible, or is allowed at compile time in constexpr context anyhow. That doesn't solve this problem though, because I have to make a bit of a compile time runtime decision. I personally think that our destructor should be treated like any other constexpr code, that anything that you do at compile time that's allowed at compile time is allowed. And if you try to do something at compile time that's not allowed at compile time, then it would fail to compile. So I could put a delete in here, and it would only fail to compile if it actually called the delete. So I'm going to skip that slide.
The wrong line is the answer.
Yeah, so throughout the course of developing this, we had problems debugging it, because actually debugging compile time errors in this kind of context can be rather gruesome. There was a couple cases where I had to remove constexpr so that it would fail at runtime instead of compile time, and then hop into the debugger and be like, oh, I had an off by one error or something, and it was difficult to suss out. So
I just had to think very hard about types.
Yes. Yeah, you had to think very hard about types. I had to think more about indexes.
Runtime, yeah.
So there's several proposals out there, all of them by David, right? So
Several
we've
by
got
David, yes.
a constexpr operator that would help you determine if something is being evaluated in a constexpr context. That could be a lot of fun for us. Constexpr trace and constexpr assert give you more debugging facility, so if something happens at compile time, you could get a message printed out. And there's someone who hacked together a static print version of this for GCC that I've played with. That was awesome.
We probably should have used that to develop this stuff. It would have cut down.
Well, yeah, but it didn't exist when we first developed this.
True, but okay. Well, earlier this year. It existed at some point, and we could use it probably.
Yeah.
That'd be really useful.
And then David also has this constexpr vector idea, which is basically the vector that I was playing with, but it can actually keep growing at compile time. So it would be a built-in thing. And also, I alluded to this earlier. So Anthony and Alexander, and I cannot pronounce their last names, have written this paper on actually implementing constexpr allocators so that we can, they made a version of vector that had a constexpr allocator plugged into it, or you could do a regular runtime allocator with it. And it works. I've seen the code. It's neat what they did, and we should probably be moving in this direction. Yes, and actually Alexander pointed that out to us after we gave the talk.
Yeah.
At C++ Now. As we already said, all the algorithms, they need to be constexpr. These three, stable cert, in-place merge, and stable partition, all have the option of allocating memory at runtime for efficiency complexity guarantees, right?
Yes.
But
the way the standard is actually written, they are allowed not to do that and fall back to a weaker complexity. So they could be constexpr, and it would technically be in line with the current standard, but of course at compile time, they wouldn't be able to offer the better complexity.
Right. We ran into some problems with iterators, but there's no reason why it couldn't all be constexpr again. So back insert iterator is not
we
enabled
wrote our own
constexpr.
back insert iterator just because we had a constexpr vector, and that was fine.
But there's no reason why that couldn't be, even if the vector itself isn't, but if we're building our other constexpr containers. So, things that should be, we mentioned swap. We did not mention exchange yet.
But it's like swap.
Yes, exchange should totally be constexpr. It's not yet. And tuple, We didn't explicitly mention tuple yet. Had the same problem with our assignment operators, back insert. All of standard array, except for the fill member function, is constexpr. That one I'm really confused about, personally. Reference wrapper, I've actually thought more about this since we put this on here.
Okay.
And I'm
You
not,
changed your mind?
I'm not positive, yes.
All right.
But it's a plausibility. Initializer lists have issues that we can't get into in the next negative minutes that we have available. Structured bindings also have things that we can't get into.
Yeah, I was actually quite surprised because, structured bindings, they're C++17, they're born into a world of constexpr. They are not constexpr.
Cannot be used in a constexpr context. Yes. And, of course, everything else. We didn't really mention this, maybe touched on it a little bit, that as we were developing this, we've noticed lots of holes in standard library implementations, even the ones that are like, we're done, we're C++17 complete.
Right. And this is by no means a slur on the implementers.
No. No.
Don't take it that way. This is just highlighting the fact that it is clear that standard library implementations basically need a doubling up of all their tests to deal with constexpr.
Yeah, and the one that I think is kind of personally a little humorous is, not a jab at the implementers at all, but that's in GCC 7.2 still, you cannot actually construct a string view constexpr because it tries to call the non-constexpr stream lane to calculate the length of the character literal that you passed
From
into
a string, you mean?
From a character literal.
What? But my regular expression thing does that.
I think you have to, if you give it the pointer and the length, it can. If you give it just the pointer.
I'm giving it the user-defined SV literal, the UDL.
That's a different constructor, I believe.
Oh, right, okay.
Yes, yeah, because that would be using the template.
That is, you're right. Okay,
So that works.
cool. So just a bare child pointer. It can't
Yes, a bare
constexpr.
const car literal it fails on.
Right.
So, flat data structures were easy for me to reason about, but once we started to get in these nested things, that became a pain. I lacked the imagination for it. Ben figured it out. Constexpr code, in a good way, forces you to think about what the lifetime of your objects are, and I'm really big about making people think about the lifetime of their objects. And like I just said, tree-like data structures are difficult to reason about for me. And if you're building your data structures, you have to select a size somehow. You can write a parser of parsers to do it, or you have to just come up with an arbitrary number at some point.
Right.
And error, that was your line item right there.
Yeah. I was getting some quite long error messages. Let's just say that.
Okay.
That's why I'm like, well, I had to go back and think about the types, and the error messages will give me a clue sometimes.
So Ben already showed how fast those builds worked, but
Yeah, this
I would
laptop's
like
about 5 years old.
Yes, I'd like to point this out. Those were not debug builds.
Right. Because in constexpr land, there's nothing to debug.
Right.
There's no runtime.
But if you're doing constexpr work in your regular full application, you might want to make a debug build. This is with GCC's numbers. GCC 7.2 still held a bit true when I was just playing with this. Basically, my laptop can't compile this in debug build. Takes 6 gigs of RAM, so it's thrashing all over swap space, depending on what I'm doing. More than 2 minutes to build, and resulted in a 338K binary. And keep in mind, this is a 338K binary that does nothing at runtime, right? Because everything was calculated at compile time.
Right. This is very dependent on the debug level.
Yes.
We found out.
Tweaking the debug level can have a huge effect.
This is a line item for compiler implementers, I suspect.
Yes. They get to do the hard work. So the release build I measured here, it was only 328 megs of RAM, not the 6 gigs. About 5 seconds on my laptop. It looked like in the ballpark 3 or something.
You saw me build it.
Yeah. 9K binary because, well, it's not doing anything. And I just wanted to make a quick comparison before we wrap this up. Anyone want to take a guess as to how long this takes to compile with GCC today? This is a full program.
Yeah, this is regular standard library, not constexpr, just using regex.
Yeah. 3 seconds, I hear? About 5 seconds. It's about the same time as compiling our stuff that's doing it all at compile time. So, We say all the algorithms can be constexpr. And standard library implementations might need some more constexpr testing.
Yes.
And
that would be a great way for anyone to contribute to standard libraries, I think. Write tests.
And you know, programming in a constexpr mindset changes the way you look at these things. Yes, CMath is not constexpr. That's a problem for some things. And let's see.
And constexpr lambdas are all powerful.
There, I will. There. All right. Sorry for taking long and starting late, but yes.
A bit longer, and thank you very much.
Thank you.
And